Alright, hello everyone. We're going to be talking about dual spaces today. So to understand what a dual space is, we need to first define linear functionals. So a linear functional is simply just a linear map from vector field to scalars. Um, and you might often see it by different names. A spoiler alert, the linear functional is also called a dual vector. And in quantum mechanics, it is called a bra, whereas a vector is called a ket. And that's because, let's say we have a linear functional v. When you put them together to make a scalar, uh, there's a bra and a ket, so that's kind of like bracket, like the angle bracket. Um, so now we can define the dual space. So we define the dual space V star, so it's a dual space of a vector space V, and it's the set of linear functionals from V to F. So now let's discuss dimension of the dual space. At least for a finite dimensional vector space, one would assume that the dimension of the dual space is exactly the same as the dimension of the vector space in question. So let's discuss that. The proof of this relies on a lemma that serves as an exercise in basic linear algebra. So if you've taken linear algebra, you probably have seen something like this before, but so based on that, lemma, uh, it's clear that the dimension of the dual space is going to be equal to the dimension of the vector space times the dimension of the fields. And this is going to be equal to 1. So that's basically it. Now you might have a question about this proof, and that is, what if the field is the set of complex numbers? Uh, wouldn't the dimension of that be 2 because there's like a complex plane? Well, the thing is, when we consider dimension in this case, we're talking about dimension with respect to the scalar. So that is, um, you know, how many, uh, I guess, basis vectors do you need? Uh, such that a linear combination of the basis factors can be any vector in the space. And as it turns out, for the complex numbers, we're not thinking about the scalars are not real numbers, and it's not that 1 and I are basis factors. It's that the scalars are complex numbers themselves, so you really only need just the scalar, and therefore the dimension in that case would be 1. I don't know if that made sense, but that's the sort of reasoning behind why dimension of the field is 1 in this case. So now let's talk about coordinate functions. And they are functionals, which we'll write as phi, such that if you have a vector like so, then phi of v takes the vector and maps it to its ith coordinate. So you could think of it like this. Let's say we have a vector v, like so. Maybe this would be phi1 of v. This vector, sorry, this vector over here could be phi2 of v. And this vector over here could be phi3 of v. As you can see, these coordinate functions are essentially taking the vector and mapping it to its coordinates. If we have like x1, x2, or something like that. We can also construct what is known as a dual basis, which is a set of functionals phi1 to phi(n), where if we have a basis e1 to en of v, then phi of ej is equal to 1 if I equals j, and 0 if I is not equal to j. This is actually an interesting function in and of itself, and it's called the Kronecker delta. Which is the function delta ij, and it equals 1 if I equals j, and 0 if I does not equal j. One can deduce that the dual basis of a basis vector, a dual basis vector of a basis vector, is equal to the Kronecker delta. So now let's discuss another theorem. So if we have a basis v1 to vn and v, and the dual basis v1 to vn, then we must have that v can be described this way. So let's prove this. We know that v is equal to c1 v1 plus dot 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 plus cn vn for some scalars, because any vector can be expressed as a linear combination of the basis or any vector in that vector space. We also know by the definition of a dual basis that when we have phi of v, that's going to be equal to phi of c1 v1 plus dot 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 plus ci vi plus dot 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 plus cn vn. And that is going to be equal to phi of c1 v1, or actually, let's do this. C1 times phi of v1 plus dot 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 plus ci vi of vi plus dot 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 plus cn vi vn. Now we know that this is going to be 0, this is going to be 0, the rest of them are going to be 0, this is going to be 1. So we end up with ci. Knowing this, we can replace each c1, or we can replace c1 with v1 of v, and each ci with phi of v. So v equals phi v1 of v plus dot 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 plus v, and this is v1 vn. And as we can see, this is our desired expression. Let's move on to another theorem, which is the following. This one is obvious from the name, but let's prove it rigorously. The dual basis of a basis of V must be a basis of the dual space. So let's see how we prove this. Suppose we have a basis and a dual basis. Suppose that we have okay, so what we need to show is that one, need to show one, the dual basis is linearly independent, and two, the dual basis spans the dual space. So okay, so let's say that we have some a1 to an that are scalars, such that we have the following expression. Now, one can verify that if we take this functional and apply it to vk in the basis, all of this is going to cancel except ak vk of vk, which ends up being ak. Therefore, since this is equal to 0, we must have that ak equals 0. Because k is arbitrary, we know that all ak must vanish. So a1 equals dot 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 equals an equals 0. So we have shown that if a linear combination of the dual basis is equal to 0, then the coefficients must be 0. So it is linearly independent. It's also pretty easy to check that the dual basis spans the dual space, because if you take a dual vector, you will be able to uh, decompose it into its constituent parts. That is a linear combination of you can basically just like find, let's say we have a dual vector phi. You can just find phi of v1. Maybe that's equal to a1, etc. Phi of vk is equal to ak. And then you can construct phi based off like so. That's basically what you want to show, but I'm not going to spend too much time with that because the second claim is pretty obvious. Therefore, the dual basis is a basis of the dual space. So now let's discuss what is known as the Dirac functional. So if we have a vector space V of continuous real functions on the interval 0 to 1, if we have some function v of x in V, the Dirac functional is defined as delta V equals V of 0. Alright, so our last theorem of the video will be the following. Suppose we have a dual vector phi corresponding to a vector v in such a way that phi of a vector w is equal to the inner product of v and w. So the map from v to phi must be an isomorphism between v and the dual space. And we're working with finite dimensional vector spaces here. So we need to prove that the map is linear first. So let's do that. So if we have a vector u plus v, then u plus v maps to phi of u plus v, which is equal to the inner product of u plus v with some vector, which by the property of linearity of the inner product is equal to this, and is therefore equal to phi u plus phi v. So that satisfies additivity. And regarding homogeneity, if we consider the vector lambda v maps to phi lambda v, which is equal to lambda v, the inner product of lambda v with some vector, which is equal to lambda times the inner product of v with some vector, which is equal to lambda phi v. Therefore, linearity is proven. So now we prove that the map is injective. So if we have that the dual vector phi equals 0, that implies that the inner product of v and w is 0 for all w in v. And so the only possibility is that v equals 0. So the map is injective. Using our earlier result that the dimension of the vector space is equal to the dimension of the dual vector space, we conclude that the map is an isomorphism. One final topic that I will discuss is that of the annihilator. So suppose we have a subset, U subset of V. The annihilator which is U naught, which is a subset of the dual space, is the set of linear functionals phi such that phi of u equals 0 for all u in U. So eventually, later in this series, we'll discuss dual vectors by a different name. We'll call them covariant. But for now, that's just, we'll just call them dual vectors. So that's it for this video. Thank you for watching, and I'll see you in the next video.